Hi friends, we're Group 39 and today we'll be walking you through our machine learning journey with the ELO Merchant Category Recommendation Challenge. Our goal, to predict customer loyalty scores and unlocking actionable insights for ELO to make personalized promotions. Let's dive in. So, what's ELO? ELO, the third largest payments company in Brazil, has issued over 132 million cards and collaborates with retailers to create tailored customer experiences. For this challenge, our mission was to predict loyalty scores based on transactional data, paving the way for meaningful and personalized promotional strategies for ELO to execute. So, this is where the fun begins. Our task was to build machine learning models to predict a numerical loyalty score based on purchasing behavior. We used the RMSE, or the root mean squared error, as the evaluation metric, with the lower scores indicating better predictions. The impact: tailored campaigns that boost customer satisfaction and retention while reducing unnecessary marketing efforts. Now, we look at the EDA on the datasets provided. This is where we faced our first challenge, that was data interpretation. The dataset had anonymized and unlabeled features, making it tricky to uncover meaningful patterns. Here, robust planetary data analysis, or EDA for short, was critical to unlocking the data's potential. We found out that loyalty scores generally followed a normal distribution, but with significant outliers, especially around the minus 33 range. This brings us to our second challenge, where these outliers could skew predictions. So, identifying and addressing them was the key focus of our modeling process. Next, we compared the feature distributions of outliers and non-outliers. Interestingly, there were minimal differences between the two groups, suggesting our third challenge of behavioral overlaps. This meant that our model needed to focus on subtle patterns to make actual accurate predictions. Analyzing transactional history over time revealed consistent trends in the test and trained datasets, with most transactions occurring actually between 2016 and 2018. This consistency further gave us confidence in the reliability of the data for building our model. We also observed similar distributions in historical and new transactions across key features. This stability highlighted the potential of relevance of these features for predictive modeling and ensured our model in the next section could generalize well. So now, exploring the lag sales features, we noticed similar distributions among the average sales over the different time lags. However, the presence of infinite values pointed to potential outliers, requiring further careful preprocessing before we could do modeling. So finally, for the last EDA, we found that while some historical transactions in blue were unauthorized, all new merchant transactions in yellow were actually authorized. This discrepancy offered another opportunity for us to refine our feature engineering process.
Preprocessing is a crucial step for data preparation. We optimize memory by converting numerical columns to efficient types, speeding up processing. Missing values were replaced with mode values to ensure data consistency and reliability. To prepare data for light GBM, categorical variables like authorized flag and category tree were encoded numerically, such as Y to 1 and A to 0. Outliers with target values below -30 were flagged for targeted analysis. Date features, including year, month, and proximity to holidays like Christmas, were extracted to reveal spending trends. These features improved the model's understanding of temporal patterns. We computed statistical summaries like mean and variance for purchase amounts, transaction amounts, and authorization rates highlighted customer activity. Categorical features used mode, while numerical features provided deeper insights. Finally, we engineered purchase patterns such as average purchase intervals and time since transactions to capture customer behavior. This resulted in 285 features, creating a robust dataset for modeling.
We will use PIM algorithm to do feature selection. We use light GBM to fit and train the model on the original target column. This will result in a data frame with a split and gain score for each feature. Next, we randomly permutate our target column and fit it on the same light GBM model. What we are doing here is we are breaking any real relationship between the features and the target, creating an importance score purely due to random chance, the null distribution score. In our implementation, we use 80 permutation. The goal is to determine if the actual feature importance score, the one in red, comes from the null importance distribution, the one in blue. This is done by calculating the ratio of the actual importance to the 25th percentile of the null importance. A high ratio indicates that the feature is likely significant, as its importance exceeds what could occur by chance. So we tested out two different types of light GBM model for the PIM algorithm. The first model uses GDBT boosting, while the second one uses Gauss boosting. For each model, we tested out different thresholds. A threshold of 10 means features with percentage importance of less than 10 are excluded from training the model to predict the target. From the graph here, we can see GDBT model of threshold 70 performs the best on our test set. It has an RMSE score of 3.67697, and this model becomes our baseline model. In order to improve the RMSE score for the baseline model, we decided to check which target value is actually contributing the most to our RMSE. We find that it is actually the outlier values causing it. The target, which is approximately negative 33, while our prediction is only 2.04. So we tried a naive approach. If our target value is less than negative 25, meaning that it is likely an outlier value, we change the value to negative 33.209, which, as shown in our EDA, is the peak number for the outlier value. This actually improves the performance of the baseline model marginally by 0.001, but this means that we are moving in the right direction to improve the model. With this, we created two new models. First is the outlier likelihood model. This light GBM model is trained using the same methodology as the baseline model, but with the target shifted from the target column to the outlier column that has been created during pre-processing. The second model is the non-outlier data model. This light GBM model is trained using the same methodology as the baseline model, but it only uses non-outlier data for training. Our first model received an F1 score of 0.197, while the non-outlier data model receives an RMSE score of 1.5, a much lower comparing to 3.67 baseline score, suggesting that by separating out outlier data, we can also predict non-outlier data better. An experiment was actually conducted to develop a third model aimed at predicting outlier data, using features exclusively selected from outlier data. However, this model underperformed, yielding an RMSE greater than 10. Thus, we decided to not use this model. So this is our final model architecture. The outlier likelihood model predicts whether a data is going to be an outlier data or a non-outlier data. If it is non-outlier, then we will use the non-outlier data model to predict its target value. If it's an outlier, then we will use the baseline model. We tested out various thresholds. If the likelihood is below the threshold, then the data is classified as non-outliers. Otherwise, it's classified as an outlier. We found that lower threshold improved performance as expected. Since the outlier likelihood model is not accurate with an F1 score of 0.197, overapplying the model trained only on non-outlier data leads to worse results. The model should only be used when we are very confident that the data is not an outlier. With this final model architecture, we have improved our RMSE score to be 3.67217.
Thank you, Joanne. Now let me walk you through how we fine-tune our hyperparameters for our models. For all three models, we utilized Bayesian optimization. So how does it work? First, we define an objective function tailored to our evaluation matrix. For the outlier likelihood model, we optimize for F1 score, while for the baseline and the non-outlier models, we use RMSE as the evaluation metric. Next, we explored the hyperparameter spaces iteratively. These are the 5 key parameters we adjusted to achieve the best possible performance while avoiding overfitting. All three models were tuned using 200 iterations, starting with an initial exploration phase of 5 iterations. While more iterations could potentially lead to a more precise hyperparameters, we faced time constraints. Each tuning session already took approximately 8 hours, and we determined that further iterations would not likely yield significant improvements. Next, let's take a look at the results. These are the hyperparameters for the baseline model, followed by the outlier likelihood model, and finally the non-outlier data model. As you can see, the hyperparameters across the models did not vary significantly. This is likely because all three models shared similar input features and benefited from the same feature engineering pipeline.
Now, let's take a look at the final result of our submission for the ELO Merchant Category Recommendation Competition. As you can see, our final submission achieved a public score of 3.67217, placing us 112 out of 4,111 submissions, meaning that we are in the top 2.7% globally based on the public leaderboards. Reflecting on our processes and results, one of the key takeaways is summarized in this conclusion. Effective machine learning models can be developed using robust feature selection techniques, even when there is no deep understanding of the underlying features. Our performance in this competition validates this principle, as much of our success relied on precise feature engineering and selection, rather than domain-specific insights. This approach not only makes modeling more accessible, but also highlights the importance of methodical experimentation in machine learning. Thank you for your attention.